Here is the combined summary of pages 14. This study constructs a stress tensor and current at null infinity in three-dimensional asymptotically flat spacetimes, leveraging the intrinsic geometry of the null boundary, which is a Carrollian geometry specified by a degenerate metric, a kernel, and a dual vector to the kernel, known as the Ehresmann connection. The stress tensor and current are canonical conjugates of the metric and the dual vector, respectively. In the context of pure 3D flat space gravity, the solution phase space is characterized by 6 functions of v, phi, namely, eta, u, omega, m, upsilon, lambda, which are determined by Einstein's equations. The remaining components of Einstein's equations impose 2 constraints, resulting in first-order equations in boundary time v and third-order derivative terms in phi, referred to as anomalous terms. The solution space is thus specified by 4 functions of v, phi, which can be conveniently chosen as m, upsilon, pi, omega. Symmetry generators, which are vector fields that move within the solution space, are parametrized by 4 functions of v, phi, supertranslations t, v, phi, superscaling w, v, phi, and superrotation y, v, phi. The transformation laws for m, upsilon, omega, and pi reveal that m, upsilon, omega, and pi are charge aspects respectively associated with t, y, z, and w symmetry generators. The authors derive the symplectic form and charges, fixing the E-freedom and boundary Lagrangian L micro b, by requiring that the symplectic potential and hence the surface charge variations are finite and independent of r. This leads to a Schwarzian action on the celestial circle, capturing the dynamics induced by reparametrizations of the celestial circle, which supports the codimension 2 holography proposed for 3D asymptotically flat spacetimes. The covariant phase space formalism is employed to derive the symplectic potential and surface charges for a Carrollian geometry. The hydrodynamic symplectic potential is rewritten in terms of a stress tensor and a null current, related to the energy, mass aspect, angular momentum aspect, and pressure. The conservation equations for the null current and stress tensor are derived, reproducing non-anomalous parts of the constraint equations, and the authors relax the torsion-free condition, distinguishing their Carrollian structure from earlier literature. Here is the combined summary of pages 58 of the research paper. The authors formulate the intrinsic stress tensor and current at null infinity, canonical conjugates to the Carrollian degenerate metric gamma ab and the Ehresmann connection Na. Conservation of these quantities leads to continuity equations for Bondi-mass and angular momentum, described by equations 36, which exhibit a Carrollian fluid with an equation of state pressure plus energy equals 0, manifesting Carrollian boost invariance. The 2,0 type stress tensor is not symmetric, sharing this trait with Carrollian EMTs. The boundary Lagrangian is fixed by the requirement of a well-defined variational principle, given by a Schwarzian action, equation 41, which captures phi reparametrization over the celestial circle. This action is invariant under time-dependent super-rotations phi right-pointing arrow phi plus y, v, phi, while being anomalous under time-dependent super-translations v right-pointing arrow v plus t, v, phi. The same boundary action can be obtained from the Gibbons-Hawking-York term at the asymptotic null boundary, equation 44, related to the Gibbs free energy density and the Frolov-Thorne temperature, equation 42. The solution space is described by 4 functions on the null boundary, specifying the stress tensor and current, and boundary degrees of freedom that form a thermal system at Frolov-Thorne temperature, governed by the Schwarzian action. The connection to the ADS 3 case is discussed, where the solution space can be obtained as the flat limit of a similar solution space in ADS 3. The authors delve into the Carrollian geometric triple in asymptotically flat spacetimes, examining the symplectic potential, which can be obtained through the flat space limit of ADS_3 results. They derive the Carrollian geometric triple compatible connection, using rescaled quantities from ADS_3 spacetime, and demonstrate how anomalous parts of the stress tensor and momentum flow can be recovered in the flat space limit, ensuring conservation. The energy momentum tensor and its relationship with the stress tensor are analyzed, highlighting the importance of the flat space limit in reproducing the Carrollian geometric triple, connection, stress tensor, and momentum flow. This paper explores the relationship between black hole entropy and its near-horizon geometry, leveraging flat spacetime holography, a specific limit of ADS, CFT correspondence. It focuses on extremal black holes, where temperature is zero but entropy remains finite, using the Carty formula from conformal field theory to compute entropy. The first law of thermodynamics plays a crucial role in connecting near-horizon geometry to thermodynamic properties. The authors discuss boundary actions, Carrollian physics, and chiral conformal field theory as tools for understanding extremal black holes thermodynamics. They also touch upon the Ashdecker variables in loop quantum gravity and the equivalence principle. The paper concludes by highlighting the need for further study on this relationship and its implications for quantum gravity and the holographic principle.